Hey team, I'm very quickly going to skip through the first couple of lessons of topic 2. So this is the first bits of 2.1 about the nuclear or the nuclear atom is 2.1 and I've done some videos already for 2.2 electron configuration. So here we go. So I'm just going to skip through these starter slides. There's a great video on YouTube of the history of the atom, and I've put this link on your OneNote so you can all have a look at it. So elements are defined as substances that can't be broken down into simpler components, which I'm sure you guys know. There are 92 elements that occur naturally on Earth, and most of them, because they're reactive, are found in some form of compound, and a lot of them are in the Earth, and we can then purify them from there. So just a brief summary here, because that great video will highlight all of this. Our idea about the atomic structure has evolved over the years as we've discovered new information, and therefore we've changed how we've viewed the atomic structure. This is a really great example of about how our knowledge can change over time, and the more experiments we do and the more evidence we gather, that builds a stronger view of what the structure of an atom is, because we can't see it. So Dalton was the first contributor, and or one of the first contributors, and he kind of thought atoms were these solid spheres, and we know that they're not, because we know that they're invisible and they're made up of subatomic particles. But you can kind of see he was the first one to assign symbols to elements, which is quite clever, and you can kind of see here what he did, which is pretty cool. Then there was Thomson's plum pudding model, which was kind of good. It had some great ideas. He worked out that there were electrons, which is pretty cool, and that there were positive charges. However, he kind of thought that the electrons were scattered through it, and same with the positive charges, so he didn't understand that there was a nucleus. Ernest Rutherford was next, and he did that really great experiment with the gold foil, and so he basically he charged alpha particles at an atom, and he noticed that what happened is that some bounced back and some went right through, and you can see that. Sorry, I don't have my pen here to show very well, so it's hard to show my cursor, but the Rutherford model, you can see that red nucleus, and you can see one of the particles bouncing backwards, and that's because it's hit the nucleus, and that happened quite often. And he also saw that they were getting deflected in different directions, and so when he mapped out, after firing loads and loads and loads, that there must be something concentrated in the middle, which is the nucleus. What he wasn't able to explain, though, is the fact that electrons move in orbitals around the nucleus. So then Niels Bohr was kind of next, and his was a really good model, and we still use the Bohr model to do a lot of our explaining in chemistry, because his model is really simplistic and we can get our heads around it, and it really suits things like periodic trends, which we're about to get to in the next topic. So it's still incredibly useful. So he basically worked out that there were quantized kind of areas where you can find an electron, so energy level 1, energy level 2, and energy level 3, which was really cool. And he worked out that you couldn't find electrons between energy levels. So that was really, really good, and he worked out that orbitals had fixed energies and sizes. So this model is really good, and it's still a great way to think of it. But he failed to... or he thought that moving electrons emit energy and collapse into the nucleus. So we now know there's a bit more of an advanced view, the quantum model, I guess you could say, by Erwin Schrödinger. And what this one does is basically that electrons move and do not move in set paths around the nucleus, but they move in kind of a wave-like structure. We don't know the exact locations of electrons, but there are clouds where we're likely to find an electron, known as the orbitals. So this is actually our current model of the atomic structure, but we often refer to this Bohr model because it's really good still, and it's still got a lot of good information. So we can see how this atomic theory has changed over time, and that's a really good example of how, like, the theory of knowledge and how it's evolved. Here's a great simulation on PhET. You have to use Chrome if you want to do this. If you just go onto Google Chrome and put Rutherford simulation, you can have a go at that. Okay, so we're going to quickly now quickly go past this stuff because I think you guys will be fine, but you guys will be aware that there are 3 subatomic particles. We know there's actually more than this, but this is all we're going to focus on because there's things such as quarks, but that's something that if you want to delve into that, you feel free to do so, but we're just going to cover protons, electrons, and neutrons in this course. So protons have a positive charge, electrons have a negative charge, and neutrons have no charge. And I know we've been doing atomic structure for a few years now, so you guys know that the protons and the neutrons are found in the nucleus in the center of the atom, and the electrons surrounded in orbitals. It's just really important to understand that the mass of an electron is really, really small compared to the mass of a proton and a neutron. You can see those relative masses there. So why are neutrons so important to our atoms? So neutrons allow the atom to actually stay together, because otherwise we'd have only positive protons in the nucleus, and we know in chemistry opposite charges attract and like charges repel. So if we only had positive protons, those protons would repel and the whole nucleus would fall apart. So now we're going to look at our periodic table, and we know there are 2 numbers. We've got the atomic number and the mass number. The atomic number is always the smaller number, and the atomic number stands for the number of protons in that atom. It also happens to equal the number of electrons, but we don't use electrons as the definition for this. The reason being is that electrons can be lost or gained, but protons never can. So protons are always the defining value for an element. And the mass number is the number of protons and neutrons. And yeah, so we probably know that. If I got you guys to do these 2 examples here, you would tell me that sodium has 11 protons because its atomic number is 11. It's got 11 electrons because we know they're the same, and the number of protons would be 23 minus 11, which is 23 minus 11, which is 12. Oh my gosh, it took me too long. Here we've got potassium, atomic number 19, so 19 protons, 19 electrons, and 39 minus 19 is 20 neutrons. So hopefully that makes sense. So what doesn't really make sense then, if the mass number is the number of protons and the number of neutrons, is how on earth can we have this decimal number? How can we have a point something of a neutron or a point something of a proton? And the answer to that is because these relative masses, and remember from topic 1, we know that these are relative masses because they're relative to carbon-12, and we talked about that in topic 1. But what we didn't delve into too much was the fact that these decimals also account for the relative abundance of isotopes. So isotopes are the same element, just a different form of them, and the different forms mean they've got different masses, and it's actually the different number of neutrons that causes that different mass. There are actually set types of isotopes, and you do get familiar with a few of these. Chlorine-35 and chlorine-37 are some of the most common. So are the bromine ones and oxygen ones, which we're going to kind of have a brief look at. So carbon-35 and carbon-37, they've both got 17 protons and they've both got 17 electrons. Chlorine-35 has got 18 neutrons though, and chlorine-37 has got 20 neutrons. That makes chlorine-37 heavier. Chemically, they're really similar because they've got the same number of electrons, and electrons are what take part in reactions. And they're still the same element because they've got the same number of protons. So the only thing that's different about these 2 is the fact that they've got different masses. So why is that significant? Well, because sometimes you'll have some chlorine-35 and sometimes you'll have some chlorine-37. So when you're doing calculations involving mass, that is going to have an impact. That's 2 atomic units different. So, or 2 mass values different, I should say. So how abundant are these? Well, if we had a barrel of chlorine, for instance, so You guys know I can't draw very well, but if we had a barrel, what you would actually find is that 75% of that barrel was chlorine 35 and 25% of it was chlorine 37. So that's if we sample just a random sample, and if we kept doing that, that would be the same occurrence that we get. So if we know the relative abundance, what's really important is we can then calculate what this number should be, which this number here is a relative abundance based on how abundant those two isotopes are. So if chlorine 35 is present 75% of the time, if we do 35 times 75 over 100, you get 26.25, and chlorine 37 was present 25% of the time, so that's 9.25, and if you add those together, you get 35.45. So that's how that value here on your periodic table, how that's come about. It's come about from how abundant those two individual isotopes are. So yeah, so the other way of looking at that is you could take the total mass of those isotopes. So out of 100, 77.5 of them are 35 and 22.5 are 37, which would give this total mass. And if you divide that by 100 atoms, you'd get the same thing. Now what you'll notice here is these values are a bit more specific, the second ones I've done, and that's because it's actually not a 75-25 ratio, it's actually 77.5 to 22.5, but these are much easier. The 75 and 25 are much easier to remember, which is why I always use those. So there are two oxygen isotopes, oxygen 16 and oxygen 18. So the only difference is that the oxygen 18 has 2 extra neutrons, making it heavier. And here we've got carbon isotopes. So we've got carbon 12, carbon 13, and carbon 14. Carbon 14 is actually used in carbon dating, and you can look that up. It's super interesting, but I won't do that on this video now. And you can see that the same number of protons, so they're the same element, but they've got different numbers of neutrons. So they're isotopes, and they're going to be heavier. You can see here there's loads of isotopes for different elements. So here's iron, and you can see some of the iron isotopes are stable and some of them are not, making them radioactive. So hydrogen, that's also the last one before we move on to ions, is quite important. You've got hydrogen 1, hydrogen 2, and hydrogen 3. You'll know by now that hydrogen 1, in fact, because you've got these two numbers here, if it's got 1 proton, 1 electron, and the mass number's 1, it can't have any neutrons. So hydrogen 1 has no neutrons, hydrogen 2 has 1 neutron, and hydrogen 3 has got 2 neutrons. Okay, moving on quickly to ions and what ions are. We've done these since middle school, so I know most of you will be really confident, but just to go over it again. So atoms that don't have a full valence shell, which is the outer shell, are said to be unstable, and so they're going to lose or gain electrons to gain stability. If an atom loses electrons, it's called a cation, and the reason for that is because if it's lost electrons, it's now got more positive protons than it does negative electrons, and therefore a positive charge. And an anion is an atom that has gained electrons to gain stability and get a full valence shell, so therefore it's got more negative electrons than positive protons and a negative charge. So the charges are always to do with the imbalance between protons and electrons. For non-metals, when they form an ion, they've got an "ide" at the end. So like oxygen forms oxide, sulfur forms sulfide, and so forth. So we can look here, and this is the calculation you would do to show the charges of an ion. So the fluorine atom has 9 protons, 9 electrons, so no charge, it's neutral, but it's also unstable because it's got one empty space, I guess you could say, in its valence shell, and so it gains an electron, and now there are 10 electrons to only 9 positive protons, and that gives it a 1 minus charge. Here we've got sodium, so the atom itself is neutral, it's got no net charge, whereas though it's not stable because it's got this electron in its valence shell, and it's easier to lose 1 than it is to gain 7, so it's going to lose that 1 electron, and that also means it loses an entire energy level, and because of that it now has got 1 less electron to proton, so a positive 1 charge. Hopefully that makes sense, and you can, if you want to, you can go through and work out what ions these would form. Okay, guys, so that video rounds up lesson 1. I'm going to do another video on mass spec and and how we use that for evidence towards relative atomic mass. So that will be the next video soon. Thanks, guys.